This section, we will look at the physical and chemical properties of the group 3 oxides. Now we will compare the melting point of the period 3 oxides. Firstly, if we look at the metal oxides, sodium oxide, magnesium oxide, and aluminium oxide, these three metal oxides have giant ionic structure with strong electrostatic forces of attraction between the oppositely charged ion. This is due to great difference in the electronegativity of the metal and oxygen. Now, they have high melting point as a result of the giant structure and strong ionic bonds. And if we look at the melting point, we'll find that the melting point increases from sodium oxide to magnesium oxide as the charges of the ion increase. This gives rise to stronger electrostatic forces of attraction between the oppositely charged ions. However, as we compare magnesium oxide with aluminium oxide, we do note that there's a slight decrease in the melting point of aluminium oxide, and this is due to the increasing covalent character in aluminium oxide. Aluminium oxide has greater covalent character compared to magnesium oxide due to the greater polarizing power of aluminium 3+ cations. Next, we will look at the covalent oxides. The covalent oxides are formed between nonmetals and oxygen. First, we look at silicon dioxide. Silicon dioxide has a giant covalent structure which is similar to that of diamond. It has a very high melting point because of the giant structure and the many strong covalent bonds between silicon and oxygen atoms. Moving on from silicon, we actually have oxides of phosphorus, sulfur, and chlorine. These are the other non-metal oxides. This group of non-metal oxide, they exist as simple molecules. And because they are simple molecules, there's only weak intermolecular forces between the molecules, resulting in them having low melting point. So if we look at the melting point of P4O6 and P4O10, we find that as the size of the electron cloud increase, the strength of the intermolecular force, which is the van der Waals forces, also increase. And hence, P4O10 has a higher melting point compared to P4O6. And the same is observed for SO2 and SO3. SO3, which has a larger electron cloud, will have stronger van der Waals forces, and therefore more energy is needed to melt the SO3 molecules. This graph shows the variation in the melting point of the period 3 oxides as you move across period 3. So generally, the metal oxides have very high melting point, with some variation as you move from magnesium oxide to aluminium oxide due to the increasing covalent character present. For the non-metal oxides, with the exception of silicon dioxide that has a giant molecular structure and hence resulting it to have very high melting point, most of the non-metal oxides exist as simple molecules with weak intermolecular forces between them. And therefore, from silicon dioxide to the next oxide of phosphorus, we'll find that there will be a very sharp drop in the melting point as the van der Waals forces between the molecules in phosphorus oxide are rather easily overcome. Now we will compare the chemical properties of the period 3 oxide. We will look at the reaction with water, with acid and base. Firstly, we will look at the metal oxide, sodium oxide and magnesium oxide. Sodium oxide and magnesium oxides have giant ionic lattice structure and they are basic oxide. However, they react differently in water. Sodium oxide reacts very vigorously in water to form sodium hydroxide, which is a strong base that dissociates fully to give Na+ and OH- ions. Because of the OH- ion produced, it gives us a highly alkaline solution with a pH of about 13 to 14. Magnesium oxide is less soluble in water because of its high lattice energy. but it will react with water to form magnesium hydroxide, which again, because of its high lattice energy, is sparingly soluble. So the little amount of magnesium hydroxide that dissolves will fully dissociate to form Mg2+ and OH- ion, forming only a weakly alkaline solution with about a pH value of 8 to 9. Now, however, because these two oxides are basic in nature, they can also react directly with acid, and they undergo neutralization reaction with acid to form salt and water. So sodium oxide reacts with HCl to form sodium chloride salt, and magnesium oxide will react with HCl to form magnesium chloride salt and water. Moving on to the next metal oxide, aluminium oxide. Aluminium oxide has a giant ionic lattice structure with significant covalent character. Unlike sodium oxide and magnesium oxide, aluminium oxide does not dissolve in water. This is because of its high lattice energy. Besides this difference, aluminium oxide is also amphoteric in nature. It is able to react with both acid and base. So in this reaction, when aluminium oxide is reacting with acid, aluminium oxide is acting as a base here, reacting with acid to form salt, aluminium chloride salt, and water. In the subsequent reaction, when reacting with NaOH, aluminium oxide is behaving as an acid and undergoes neutralization reaction with sodium hydroxide to form sodium aluminate. Moving on, we will look at the reactions of the non-metal oxide. Silicon dioxide is a giant covalent compound with many strong covalent bonds between the silicon and oxygen atom. So therefore, it does not dissolve in water because too large an amount of energy will be needed to break the many covalent bonds in the structure. Being a non-metal oxide, silicon dioxide is acidic and can undergo reaction with base. So in this reaction, we find that silicon dioxide can react with NaOH to form sodium silicate and water. However, for the reaction to take place, do note that hot concentrated base is needed, as silicon dioxide will not react with aqueous NaOH. The oxides of phosphorus and sulfur are simple covalent molecules, and being non-metal oxides, they are acidic in nature. P4O6 and P4O10 reacts readily in water to form acidic solution. When P4O6 reacts in water, it forms phosphorus acid, and when P4O10 reacts in water, it forms phosphoric acid. So these two acids dissociate in water to form H+, resulting in the pH value of 2. The oxides of sulfur, such as SO2 and SO3, also reacts readily in water. When SO2 hydrolyzes in water, it forms sulfurous acid, H2SO3, and when SO3 reacts in water, it forms sulfuric acid, and this acid dissociates to form H+, resulting in an acidic solution of pH 2. These two non-metal oxides, being acidic in nature, they can also be reacted with directly with base, and they undergo neutralization with base to form the corresponding salt and water. So if we have P4O6 reacting with NaOH, you will form the salt, Na2HPO3, and water molecules. This graph here shows the pH of the resulting solution when the period 3 oxide reacts in water. So for sodium oxide, it reacts vigorously to form NaOH, and therefore the resulting solution has very high pH of 13 to 14. MgO, magnesium oxide, will react in water to form magnesium hydroxide, which is sparingly soluble, and therefore the pH value of the resulting solution is only slightly alkaline, 8 to 9. For aluminium oxide and silicon dioxide, due to their strong chemical structure, you will find that they are insoluble in water, and therefore the pH of water is not changed. For the non-metal oxide, they tend to hydrolyze in water to form an acidic solution, as acids are being formed in the reaction, and some of the acids that will form include phosphorus acid, phosphoric acid, sulfurous acid, and sulfuric acid. And these acids dissociates in water to form H+, giving us a very acidic solution with low pH values. This table here summarizes the variation in the physical and chemical properties of the period 3 oxide.